Infinite Possibilities Conversation. After exploring quantum reality and computing fundamentals in earlier sessions of Quantum Think series, they're now ready to dive into real-world applications. Natalie Dawson kicks off their third conversation with palpable curiosity. Joseph, last time was mind-bending. We talked about how quantum thinking shifts our perspective from certainty to probability, or, as you brilliantly put it, possibility to probability to event. That idea really stuck with me. Reality as a dance of possibilities, collapsing into events. Today, I'm eager to get practical. How does that core insight translate to something tangible, say in my field, finance?
Excellent question. The shift from cause and effect to possibility-probability event isn't just philosophy. It underpins how quantum computers operate. Think of a quantum computer as a machine that engineers probabilities. It sets up a vast space of possible answers, possibilities, then interferes with them to amplify the probability of the answer we want, before finally measuring an event, the outcome. In finance, where we often face huge possibility spaces, all the ways to allocate a portfolio, all the potential fraud patterns, all arbitrage routes, this quantum approach can be a game changer.
It sounds promising, but also abstract. Let's ground it. I've heard of Grover's algorithm as a key quantum method. Isn't that about searching for a needle in a haystack?
Exactly. Grover's search algorithm is a famous quantum routine, and it's tailor-made for the needle in a haystack problem. In classical terms, if you have n unsorted possibilities and one needle solution, finding it might take up to n checks in the worst case. Grover's algorithm, however, can find the needle in about square root of n steps. That's a quadratic speedup, not exponential, but still massively faster when n is huge. Imagine searching 1 trillion possibilities in roughly 1 million steps instead of 1 trillion.
How does Grover's actually achieve that? Are we just magically skipping checks?
It's not magic, it's quantum interference. Let me use an analogy. Imagine a giant warehouse of boxes in the dark. One of those boxes has the financial prize you want, say, the perfect portfolio or a fraudulent transaction record. The needle. Classically, you'd stumble in the dark opening boxes one by one. A quantum computer does something spookier. It effectively opens all boxes at once in a superposition, a massive simultaneous exploration.
Now, obviously, you can't directly see the answer from a single measurement of that superposition. It would just give a random box. This is where Grover's cleverness comes in. It uses an oracle, essentially a yes/no checker, that can recognize if a given box is the prize. Think of the oracle as a friend with a flashlight that glows only when you've opened the winning box. Grover's algorithm does 2 steps repeatedly. Mark the correct possibility with the oracle, make that winning state glow, or invert its phase in quantum terms, and then interfere all the possibilities such that the marked one's probability amplitude gets amplified, while the rest get dampened. It's like each round of Grover's algorithm turns up the brightness of the right box and dims the wrong ones through interference. After enough rounds, about square root of n, the winning box is brighter than all others. You measure the quantum state, and bingo, you found the needle.
So the oracle is basically a filter. It doesn't tell you where the needle is directly. It just says, yes, this is it, for a given guess.
Precisely. I like to say the oracle is a checker, not a prophet. It's not gazing into the future to deliver the answer. It's more like a strict validator. If I present a candidate solution, the oracle returns true, or gives a special marking phase, if that candidate meets the criteria. Otherwise, false. In Grover's algorithm, we embed that oracle into the quantum circuit. We're effectively querying all candidates in superposition, and the oracle marks all the correct ones at once. There might be one needle or multiple needles. But here's the twist. Because of quantum superposition, the oracle check doesn't collapse the state outright. It just flips the phase of the good states. Then the algorithm's interference step uses that phase info to amplify those marked states' amplitudes.
It's like you have a metal detector that beeps whenever you sweep over the needle, but you sweep over everywhere at once, and each beep constructively interferes to make the needle's location stand out louder and louder.
Exactly. The warehouse analogy with a glowing box, or a haystack where the hay dims and the needle shines brighter with each pass, captures it. After enough sweeps, the needle's probability of being picked is so high that one measurement will find it. Grover's is one of the most dramatic illustrations of exploiting possibility and probability in quantum computing. Great. Now I see how it works in principle. Let's connect this to finance, as you mentioned. Finance problems aren't literally about searching an unsorted database. Or are they in disguise?
Many are in disguise, yes. In finance, we often face combinatorial search problems. Essentially, find an X that meets condition Y. That's Grover's home turf. Let's discuss a few use cases in finance where Grover's algorithm, or quantum search, could help. 1. Portfolio search under constraints. Imagine searching through all combinations of assets to find a portfolio that meets certain criteria. For example, a target return of 8% with risk below 5%, or a valid allocation that obeys dozens of regulatory and budget constraints. The space of possibilities is enormous, exponential in the number of assets, a haystack of portfolios. Quantum search could speed up finding a feasible or optimal portfolio by treating each possible portfolio as a box to check too. Fraud detection, rare pattern matching. Financial frauds can be like hidden patterns, maybe a particular sequence of transactions or a network of accounts triggers a red flag. Scanning millions of transactions or account links for a rare, complex pattern is a search problem. A quantum algorithm can quadratically speed up scanning transaction records for anomalies or fraud pattern. Essentially, label each transaction or set of transactions as fraudulent or not via an oracle that checks the pattern, then use Grover's to find the ones that return yes. 3. Arbitrage and trading opportunities. In trading, finding an arbitrage, a sequence of trades across markets that yields a profit with no risk, can be like searching for a secret path in a huge maze of prices. There may be thousands of instruments and connections. Grover's search could, in theory, be used to find an arbitrage route or optimal hedge much faster by checking many possible trading paths in superposition. If an oracle can verify this set of trades yields profit above X, Grover can amplify that path.
These are compelling. Let's unpack them one by one so I fully grasp how Grover's would be set up in each case. Starting with portfolio search, how would a quantum computer find a portfolio? Isn't that more of an optimization problem than a straight yes/no search?
Good point. Portfolio optimization is usually formulated as maximize return for given risk. But we can turn it into a search by looking for a portfolio that meets a defined goal. For example, search for any portfolio that has return greater than or equal to R and risk less than or equal to sigma. That's a yes/no condition for any given portfolio. Does it meet the thresholds? We construct an oracle for that. Input a possible portfolio, a combination of assets with certain weights, and the oracle checks the data. Yes, this portfolio meets the target return and risk, or no, it doesn't. If we allow some tolerance, there might be multiple portfolios that satisfy the criteria. Grover's algorithm can actually find one of the satisfying portfolios in square root of n time, where n is all possible portfolios, which is astronomically large, but bear with me on scaling. In a proof of concept, researchers used Grover's algorithm on a toy universe of, say, 5 assets. That's 2 to the power of 5 equals 32 possible subsets if you only choose inclusion/exclusion, and successfully found an optimal subset meeting a target. They set up an oracle marking any portfolio that exceeded a certain return and had bounded risk, and Grover's search pulled out the winning combination faster than brute force. Of course, for real markets with many assets, we can't enumerate everything yet. Current quantum hardware is too small, but it shows the principle. In the future, a quantum search might comb through trillions of portfolio combinations to spot the ones that meet a fund's exact needs, far quicker than classical exhaustive search.
That's amazing to imagine, like having a quantum assistant rummage through every possible investment mix overnight and coming back with, here are the portfolios that achieve your target and obey all 100 constraints you had. It's a very different approach from today's heuristics or greedy algorithms. Moving to fraud detection, how is looking for fraud a search problem? Usually we use machine learning to detect fraud by learning patterns. What would Grover do differently?
Think of fraud detection as finding the proverbial bad needle in a haystack of transactions. Say we have a specific rule or pattern that indicates fraud. For example, a set of accounts trading money in a circular fashion to launder funds. If that pattern is well defined, we can create an oracle. Input a candidate set of transactions or accounts, and the oracle outputs yes if they match the fraud pattern, like the accounts form a loop exceeding some dollar threshold, occurring within a short time frame, etc. No if not. Classically, to find that pattern, you might have to test a huge number of combinations of accounts or transactions, which is infeasible in real time. With Grover's algorithm, you prepare a superposition of all possible combinations within some bounds, and use the oracle to mark those that match the fraud pattern. After a few interference rounds, a marked combination, meaning a concrete example of fraud, will be highly amplified. Measure the quantum state, and out pops a suspicious transaction sequence that fits the rule. To clarify, quantum won't intuitively understand fraud. It's following a rule we give it. But it can search the space of possibilities far faster than brute force. Research suggests that leveraging amplitude amplification, the core of Grover's algorithm, could flag anomalies or fraudulent transactions faster than classical scanning. For instance, one proposal showed quantum amplitude amplification might identify rare fraudulent patterns with fewer samples than classical methods, meaning catching fraud in something like real time could become feasible.
If I understand, this would be extremely useful for something like credit card fraud or anti-money laundering. Those often rely on rules, like transaction bursts or amounts, that are simple individually but complex in combination. Grover's could, in principle, check all combinations of events in parallel to find ones that fit a complex rule, something a normal system would choke on. Now, arbitrage. I am particularly interested in that as a trader. Arbitrage opportunities can disappear in milliseconds. How would a quantum search help here? Isn't arbitrage detection more about speed and data feeds?
High-frequency trading firms already scan for arbitrage with ultra-fast classical algorithms. But as markets get more complex, imagine looking for a multi-leg arbitrage involving several assets or across many exchanges. That could be considered a combinatorial search. You're looking for a sequence of trades across, say, 5 different markets that starts and ends with the same asset or currency and yields a profit. The search space might be huge if you allow various lengths of sequences and different instruments. Grover's algorithm could drastically reduce the search time for such a profitable route. If the oracle can evaluate, yes, this cycle of trades yields net profit, then Grover's will amplify those yes instances. Essentially, instead of your algorithm doing depth-first or breadth-first search through a graph of prices, a quantum computer could wander all paths simultaneously in superposition and mark the winning path. After interference, measuring gives you one of the winning arbitrage routes with high probability. One article put it succinctly: searching for the best arbitrage or hedge opportunity is computationally intense. Grover's algorithm can cut the search time from n steps to roughly square root of n. That could mean finding a market inefficiency before it's gone. Of course, quantum hardware latency is an issue today, but in principle, this is where a quantum advantage could manifest, by beating others to the discovery of an opportunity, provided others aren't also using quantum at the same time.
Right, a future where traders have quantum assistants scanning all markets for a fleeting profit loop. The playing field would change dramatically. I notice a pattern. In all these cases, the quantum approach still needs us to define the problem and the oracle properly. It's not predicting the best portfolio from scratch or spontaneously knowing what fraud looks like. We provide the criteria. Quantum computing then turbocharges the search given those criteria. Maybe you can walk me through a concrete scenario, say in fraud detection, showing how a hybrid quantum classical system might actually work. It would help me visualize the integration.
Certainly. Let's imagine a concrete fraud detection system that uses both classical and quantum components in tandem. Step 1. Classical data preprocessing. A classical server is continuously aggregating transaction data, say millions of transactions per hour streaming in a bank. It does the usual things first, filtering obvious red flags with classical rules and preprocessing data into a format the quantum part can use, perhaps encoding transactions as binary strings or qubit states. Step 2. Define the oracle. Classical logic. The fraud analysts have given a rule. For example, if more than 5 accounts are involved in a circular series of transfers, totaling over $1 million within 24 hours, flag it. This rule is translated into an oracle circuit. Think of it as a small classical subroutine embedded into a quantum gate sequence. It checks a batch of transactions and outputs 1, true, if they fit the fraud pattern, 0, if not. Designing this oracle is crucial. It's like programming the criteria into quantum-friendly form. Step 3. Quantum search. Grover's algorithm. Now the quantum computer takes over for the heavy lifting. It initializes qubits into a superposition of all possible combinations of transactions, or all subsets of recent transactions up to a certain size. This is a huge search space. Potentially every way 5 or 6 transactions could be linked. Then it applies the oracle quantumly, marking any combination that constitutes fraud, the glowing fraud sequences. Then the Grover diffusion operator amplifies those marked combinations' amplitudes. It repeats the mark and amplify loop a number of times, optimized for the fraction of solutions expected. Step 4. Measurement and verification. The quantum computer measures the qubits, collapsing the state to one specific combination of transactions, ideally one that the oracle marked as a fraud. This result, maybe it's a set of transaction IDs, is sent back to the classical system. The classical system then verifies the found pattern in the full database, the double check, since quantum algorithms have some probability of error. If confirmed, it can trigger an alert. Hey, these transactions form a suspicious loop, likely fraud. Step 5. Action and learning. Finally, the classical side takes action, maybe freezing those transactions, notifying compliance officers, etc. It could also log the pattern and perhaps feed it into a machine learning model for broader analysis, combining the best of both worlds. Quantum search finds an example quickly, ML generalizes patterns for future. Throughout this, notice the synergy. Classical computing handles data and defines the problem, and quantum computing accelerates the solution search. The result is a near real-time fraud detector that might catch complex schemes that evade normal detection. In theory, what might have taken days of exhaustive search or wasn't feasible to detect at all, a quantum computer could find in minutes or seconds.
If I understand, this would be extremely useful for something like credit card fraud or anti-money laundering. Those often rely on rules, like transaction bursts or amounts, that are simple individually but complex in combination. Grovers could, in principle, check all combinations of events in parallel to find ones that fit a complex rule, something a normal system would choke on. Now, arbitrage. I'm particularly interested in that as a trader. Arbitrage opportunities can disappear in milliseconds. How would a quantum search help here? Isn't arbitrage detection more about speed and data feeds? That step-by-step makes it clear. It's almost like the classical computer is the project manager breaking down the task, and the quantum computer is the genius intern who can sift through absurd amounts of possibilities in a flash, given a well-defined task. I'm also thinking about the comparison with AI/ML models. In fraud detection today, as I mentioned, we'd often train machine learning models on past fraud data to predict new fraud. How does the Grover approach compare to AI? Are they complementary?
They can absolutely complement each other, but they are different tools. Here's a comparison to clarify. Nature of approach. Machine learning, ML, is statistical and predictive. An ML model might analyze historical data of fraud versus legitimate cases, and then predict the probability of new transactions being fraudulent. It excels at finding patterns implicitly, even if we don't know the exact rules. However, it can produce false positives/negatives, and often works like a black box. You don't always know why it flagged something. Grover's algorithm is deterministic search. It needs a clear definition of what it's looking for, the oracle. It doesn't learn from examples, it brute forces smarter. So it will find what you ask it to find, if it exists, and if the criteria are off, that's on the human who coded the oracle. When useful. Think of ML like a sniffer dog. It's trained on a scent, past fraud patterns, and can sniff around and bark when something smells similar to what it learned. It might even catch new variants if they smell close enough to known patterns. But it might miss completely novel schemes or bark at innocence, false alarms. Grover's is like a precision spotlight. You tell it exactly what pattern to shine on. Find me a loop of transactions doing X, Y, Z, and it will scour every corner quickly and light up an example of that pattern if one exists. It won't catch things outside that pattern, but if a fraud falls in the defined category, Grover's won't get tired or miss it by chance. It will find it with mathematical certainty, assuming ideal conditions. Computational performance. Today's ML can handle huge data by training on GPUs, etc. But some combinatorial problems, like an exhaustive rule-based search, are just not tractable classically. Grover provides a quadratic speed boost for those kind of exhaustive searches. If you had an ML model that still requires scanning many possibilities, some anomaly detection does this, a quantum approach could reduce that load significantly. On the other hand, Grover's algorithm needs quantum hardware and is currently limited by qubit count and noise, so ML is more practical right now, except for small demonstrations. In short, use ML when you don't have a clear rule or want to discover patterns from data. Use quantum search when you have a defined condition and need to find a needle that classical methods would take too long to find. In the future, We might even see hybrid systems. ML could propose likely patterns or narrow down the search space, and then quantum algorithms zero in to verify and find actual instances.
That makes sense. It's not an either/or, but a toolbox. The dog can sniff out general suspicious areas, and the quantum spotlight can then thoroughly scan the area to confirm something is there, or vice versa. Now, stepping back for a moment, hearing all this, I wonder, what does quantum advantage truly mean in finance? People often hype quantum computing as this crystal ball for beating markets or something. From what we've discussed, it sounds more nuanced, not predicting the future, but rather accelerating useful discoveries. How would you frame the real promise?
You hit the nail on the head. The real quantum advantage in finance likely won't be a magical fortune teller that predicts stock prices better than any model. The markets are too noisy and complex, and as we learned in part 1, even nature doesn't allow perfect predictions due to chaos and quantum uncertainty. Instead, quantum advantage will appear in computational tasks that are currently painfully slow or impossible on classical computers, but are valuable when solved quickly. It's about speeding up what we already attempt to do, or enabling us to do things we dream of doing but can't at scale. For example, finding an optimal arbitrage or portfolio configuration among astronomical possibilities. That's a discovery task. Or calculating risk scenarios with Monte Carlo simulations, much faster using quantum sampling. Or quickly searching through encrypted transaction records when investigating financial crimes. These are places where quantum algorithms could provide a practical edge, doing in minutes what might take classical computers years. Crucially, quantum computers won't violate the fundamental unpredictability of markets. They won't tell you with certainty what stock to pick tomorrow. What they can do is, for instance, explore an incredibly large set of investment possibilities to find one that meets your criteria, effectively expanding what is computationally reachable for decision makers. It's akin to giving analysts a superpower, not foresight, but ultra-fast hindsight across myriad scenarios. In finance, that means better optimization, faster detection, more comprehensive risk analysis. For instance, instead of running 10 million Monte Carlo scenarios for a portfolio, maybe you can run billions or use quantum algorithms to get the same accuracy with far fewer samples, thus pricing a complex derivative in seconds where it used to take hours. Or, as we've discussed, checking through all transactions for a cunning fraud scheme in real time, rather than flagging it after the fact. So the quantum advantage is about acceleration and scale, not mystical prediction. It's about aligning with the quantum mantra of possibility to probability to event by broadening the possibilities we can practically consider, biasing probabilities toward the outcomes we care about, and then making those outcomes happen faster or more efficiently. It's making the search for value or risk or opportunity incredibly efficient.
I like that perspective a lot. It's more grounded. Rather than expecting a crystal ball, we're looking at a turbocharged engine for financial computations. It can't see the future, but it can dig through the present's complexity at unprecedented speed, giving us insights or solutions that were out of reach.
Well said. And that's where the excitement truly lies, in augmenting human decision-making and classical models with a quantum boost. It's the difference between trying every key on a giant keyring one by one versus using a quantum lockpick that can try many keys simultaneously and open the lock faster. The lock still has to be designed by us. We decide what door to open, but we get through it more swiftly.
This has been illuminating. To wrap up, what do you think is next on the horizon as we merge quantum theory and finance?
We're at an early stage. In the coming years, we'll see more quantum hybrid systems solving toy models of these problems, like small portfolio optimizations, simplified fraud networks, mini arbitrage between a few currencies, as proofs of concept. As hardware improves, those will scale up. Financial institutions are already investing in understanding these algorithms, so when quantum hardware is ready, they can deploy solutions quickly. I foresee quantum computing becoming a part of the financial toolkit, working alongside AI and classical algorithms. And philosophically, I think finance professionals will start to adopt more of that quantum mindset. Instead of asking, what will happen in the market, they'll ask, what can happen and how can we leverage those possibilities? Very much the shift from prediction to preparation. That's quantum thinking applied to finance. Embracing uncertainty, exploring possibilities rapidly, and using that to make robust decisions.
Fantastic. So the universe might not give us certainty, but with quantum tools, we can at least explore uncertainty faster and deeper than ever before. It's a fitting continuation of that theme. We can't control events, but we can control the conditions and harness probabilities to our advantage, even in something as human-made as financial markets.